This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Where I left off last time and tell you that the pressure rise across the shock divided by the pressure upstream of it depends on the M. If it were a normal shock, it would be m1 squared minus 1, and m1 is if you have an oblique shock, it's the normal component of the Mach number, m1n, which was m1 sine beta. So this was the pressure rise, and last time I worked out for you what the tan of the angle, if you deflect the flow through an angle through this oblique shock wave. So behind the shock you have a different u, the same v, so you have a different angle. And I worked that out last time, and this was the expression for tan theta as a function of beta and m1. Now, if I wanted to work out the small weak shock wave limit, so I'm going to deflect the flow through a tiny angle, then my tan theta becomes just theta in radians. And this expression becomes, so what I can do is I can substitute m1 squared sine squared minus 1 for the pressure rise. So I have 2 over gamma plus, so let's just think about that. So theta is equal to this denominator here, and I'll have 2, and then I'll have m1 squared sine squared minus 1, which I can write from here from the delta p, and that's gamma plus 1 over 2 gamma by 2 delta p over p times this denominator here. Now I want to work out, so this is weak shock waves. I want to work out what this denominator is. So I have to suppose that my normal shock Mach number is just a little bit more than 1. So m1 squared sine squared beta is 1 plus epsilon. So 1 minus 2, which is what I need down here, 1 minus 2 sine squared beta, will be 1 minus, and what is sine squared beta? Well, if epsilon is small, it's 1 upon m1 squared, so 1 minus 2 over m1 squared. So now let's draw this out. So here's beta. So if I take m1 sine beta is 1 plus epsilon to the 1/2. So here's a triangle. So 1 plus epsilon to the 1/2 divided by m1 is sine of beta. So I can just use a square for this is a right angle here. I can just use Pythagoras. And what's the length of this side here? Well, it'll be the square of it will be this squared minus that squared. So that's m squared minus this thing squared, which is 1 plus epsilon. So minus 1 plus epsilon is minus 1 minus epsilon. And it's the square root of that, which is the length of this side. So the tan of beta is 1 plus epsilon to the 1/2 over this thing. And if epsilon is a very small quantity, then that's tan of beta is 1 over the square root of m squared minus 1. So I can put this into here, into this expression. I cancel the 2's, and so theta is equal to delta p over gamma, gamma plus 1. And now this tan beta is going to be 1 upon the square root of m squared minus 1. So it's up here in the numerator, and then I've got this quantity here. And if I work this out, I have 1 minus 2 sine squared beta. I can work that out, and this is here. And so this is m1 squared into gamma minus plus 1 minus, no, wait a minute, 1 minus 2 gamma squared. So this is m squared minus 2 over m1 squared. And so I've got a gamma m1 squared in here, and then the m1 squared for this term here will cancel with this when I put that into there. And I'll have a gamma plus 1. And that gamma plus 1 will cancel with this one here. So there's just a little fooling around to be done here, and the 2's subtract. And so I have this expression, and so it becomes really rather simple. Theta is 1 upon gamma delta p upon p, the square root of m squared over m1 squared, and that gamma plus 1 cancels from here. All right, so this is the weak wave solution where I have a very small pressure rise for a very small turning angle. And we're going to need that. We're going to use that. But one of the things that it does is tell you about what is called the shock polar. And you saw me draw a shock polar earlier where I drew theta versus beta. And I had different curves. Well, now I'm going to change it into something different. Firstly, so this delta p over p goes like this quantity here. All that I've done is write the line above. I worked this out for theta, so, and I've got a delta p over p, so I can write an expression for delta p over p, which will be gamma times theta. m1 squared will go up over there, and this square root of 1 minus n squared goes in the denominator. So that's the weak wave solution. Very small pressure rise for a very small turning angle, theta. So that's shock polar. So now you can see, if I take this p over to the right-hand side, and then I can write, that's gamma p. Well, gamma p, you know, is rho a1 squared. So if I divide by the rho, I've got a rho one here, and then if I divide by u1 squared, I'll have u1 squared in the denominator and a1 squared in the numerator, and that'll cancel with this m1 squared. And I've got rid of the gamma, and so and that 1/2 will give me a 2 over here. So that gives me, if I write delta p and I non-dimensionalize it by a half rho u1 squared, then I get something interesting. It's 2 theta over the square root of m1 squared minus 1. So this is the weak wave solution. So it's way down in this region here. So delta p over q is 2 theta over m1 squared minus 1. So this is a linear range here. For small theta, this is a linear, and I haven't drawn it very well, but it should have been linear here. And then there's a maximum value. Theta is a maximum value. And then what's the limit for a strong normal shock? Well, that's easy. So let's just go up. So if I have a very strong normal shock, then beta is pi on 2. So I'm coming in normally to the shock. So that's pi on 2. So this becomes m1 squared minus 1. So if I take this p over here, I write gamma p, and that's rho a1 squared. So I can put the rho down there, and if I put a half out in front, that'll put a 2 up there. I've got to multiply this side by 2, so I'll have a 4. The gamma p is rho a1 squared. And so there I've got an a1 squared divided by a u1 squared if I divide this by a half rho u1 squared. And so I get 4 over gamma plus 1 and m1 squared minus 1. So that is the so strong shocks, theta equal to pi on 2, delta p over q is 4 over gamma plus 1, m1 squared minus 1 over m1 squared. So if I take m1 to going to infinity, an enormously strong shock, the maximum value of this quantity here is 4 over gamma plus 1. Even though m1's going to infinity. So that's why, but in general, it's not 4 over gamma plus 1, it's 4 over gamma plus 1, m1 squared minus 1 over m1 squared. So if m1 was, say, 2, this is 4, this is 3 over 4, so it's smaller than 4 over gamma plus 1 for the normal shock. So we're going to use that. So this is what happens as this shock polar, as you increase m to m going to infinity, you go to 4 over gamma plus 1. For m less than that, it's delta p over q1 is less than 4 over gamma plus 1. So these shock polars for different Mach numbers look like this. And this is the weak shock limit that I've worked out.
There's 2 branches of the solution, right? So
Yes.
for a given theta, there's 2.
For a given theta, there's 2 possible branches.
Yeah.
One of them is supersonic, and the other is subsonic.
Yeah. So it has some relevant or some comparison with the theta beta m charts.
Yes, it is. This is nothing more than the theta beta m chart, but it's recast. It's recast into what is commonly called the shock polar, and I'm going to show you why people worry about it or use it.
But it's interesting that just a small increase in angle at the critical point and the delta p over gamma plus 1 shoots right up. I'm saying, see how you see the edge of the curve? There. Just a small increase in angle.
Oh yes, a small increase in angle can take you to subsonic flow or supersonic flow. Yes?
How can I read beta from this plot?
I can't get beta from this plot. I have to go back to the other plot. So you could get a table for theta as a function of Mach number and beta. So if I'm given Mach number and given theta, I could get beta.
But for gamma over gamma plus 1, it's only happening for 90, right?
No. The oblique angle, you can have an oblique angle for arbitrary Mach number. And you can turn the and you can get the strong solution, which is subsonic behind the shock, or supersonic behind the shock, if I turn it a small amount.
Yes, but I mean, for delta B over Q, it's only to be gamma over gamma plus 1, it's only true if beta is 90.
Yes. Otherwise, it looks like this. It looks like this is the shock polar. So for theta, only for theta equal to 0, this is a normal shock, and that's the maximum value of delta P over Q. And that's the strongest possible shock.
The top half of the branch is a supersonic solution.
The top half is, this is
Oh, sorry, yeah. I don't
M2 less than 1.
Yeah, sorry, I'm taking my glasses.
Yeah. So strong shocks also have theta equal to 0, beta is equal to pi on 2, and the flow doesn't get turned at all. And behind the strong shock is subsonic flow. All right, so now I want to give you a couple of examples. let's take the simplest example first, where I have a supersonic flow in this duct. So this is the intake to a gas turbine, for example, and I want to have a subsonic flow going into the turbine. So I've got to go through a series of shock waves, but I don't want to go through a normal shock because I lose too much entropy. I gain too much entropy. I lose too much total pressure. So I want to do it through a sequence of turning. So let's work out the simplest case here, where this angle is this angle. So I have a region 1 here and a region 2 here. So if I turn this flow by this amount, top and bottom, then I have my shock polar. I have delta P over Q for whatever this Mach number is. If it's not infinite, it goes up here to a maximum value. And but I'm just going to turn it here, and so my angle theta, I'm going to turn it through a negative angle on the shock polar, and I'll finish up here. And the same would be true in this region here. And now I want to go, so that would be on this side. But now I want to go to my region 3. So by symmetry, what I'm going to have is this flow going up and this flow going down. So in order to get something sensible, I'm going to have the same direction for the top and the bottom. And so the flow is going to turn back, and it's symmetrical. The flow is going to turn back horizontal. So if I'm going this way and then I have to turn horizontally, I have to go through another shock wave here. So this is a shock wave here, and there'll be a shock wave here that's going to turn this flow from going in this direction back to horizontal. So I draw my shock polar for this region here, and now I'm going to have to turn the flow, and I'm going to have to turn the flow from whatever it was here back to 0. So here's my shock polar based on a new Mach number here, and I turn it back to 0. And that's my region 3, top and bottom. So that's how you could do it. That's how you would do it. And, okay, so what is actually going on? If I have an M1 here and I know theta 1, that gives me beta, because I get the theta is a function of Mach number and beta. So that gives me a beta 1, 2, the angle of this shock here, the bleak shock. And that also gives me the Mach number in this region 2. I can get this region 2 Mach number in there.
Is it normally a strong or weak shock?
What I'm doing here is a weak shock, because I want a supersonic. This is still a supersonic flow here. I don't want a subsonic flow. So I'm just reducing the Mach number from 2.5. So we're talking about, say, the Concorde. And I'm wanting to reduce the Mach number slowly in this inlet region. I don't want a strong normal shock. So I want to do it through a sequence of relatively weak shocks.
So why the flow has to be horizontal after the
At the center line?
Yeah.
Because symmetry would demand, well, there are two reasons. One of them is that I've got to match the pressure across this imaginary discontinuity here. Now, in this particular case, there's no discontinuity. In what I'm going to show you in a minute, there will be a discontinuity in velocity and temperature. But in this case, since the flow below the center line is exactly the same as the flow above it, you'll have symmetry here, so whatever you have here, you'll have to have here. And the only solution that's compatible is that you have horizontal velocity. And I can easily achieve it. I can easily achieve that by turning this flow from this direction to horizontal through a shock wave. So this shock wave here is transmitted into this region here, and that shock is slightly different from this shock. This shock is slightly different from this shock. And then now the flow is going horizontal, but here I have to turn the flow again. So I have to, that's like this region here, I have to solve for this problem as well. So I have another oblique shock there. So I reflect this shock here, and I have another shock. So you can see I have a whole set of shock waves. It takes me back finally to subsonic flow. All right, so what I've said here, that M1 and theta 1, this angle here, give me a beta 1,2 and a Mach number in region 2 here. And that region 2 and the fact that I have to turn the flow back to horizontal gives me a beta 2,3. And I can get an M3 and I keep on going. So it's very much a local solution. And it's a solution that you can construct totally different from subsonic flow. Totally different. You have shock waves in this particular case, the way I've drawn it. And I'm using the shock polar for you to see how it works, what you're really trying to do. You're turning the flow each time. So you have separate regions. In this region, the flow's going this way, everywhere. Behind this oblique shock, everywhere the flow's going this way in this region. And then I have another region where the flow is going this way, horizontally, everywhere inside that region. And now I have another shock wave where everywhere in this region I have the flow going this way. And now it has to turn horizontal again. And so I keep on going through a diamond, set of diamond shock waves. All right. Now I want to talk about compression and expansions by turning the Prandtl-Meyer function. Okay, so now you can begin to see how I've used earlier parts of this course to set things up for me later. And what I've just done, I've shown you that the pressure rise across a weak shock is gamma m1 squared theta over the square root of m1 squared minus 1. So for m1 greater than 1, the pressure rise, I turn the shock and I get a pressure rise. Now, however, for a single shock, the entropy change is proportional. You'll remember that I showed you that the entropy change across a shock was proportional to delta P over P all cubed. All cubed. So that was a very interesting and important result. And what can we say about it? Supposing we had a single shock, the entropy change would then be proportional to delta P over P cubed. And if we were to use this formula, it would go like theta cubed. However, what if instead I compress the flow through n steps that are only delta theta? And delta theta, so I'm going to have n steps of delta theta where n delta theta is equal to theta. So think about that. I'm just making n steps for each small angle delta theta until I finally turn the flow theta. So what this would mean is that after n steps of delta theta, Pn minus P1 would go like n delta theta. and then that would go like theta. So the pressure goes like theta, but what about the entropy? So the entropy after n of these steps will be, I'll have n steps, and how much does the entropy change for each step? Delta P over P cubed. So that goes like delta theta. Each one of these steps goes like delta theta cubed. But delta theta is theta over n. So if I cube that, I get theta cubed over n cubed, and I have an n here. So that's theta cubed over n squared. So that's interesting. That's interesting. If I took n to infinity, then the change in entropy would be 0. So if I have a whole lot of shocks, I'm better off than having just one. My entropy doesn't change. So that's the basis. Thus, increasing the number of steps reduces the entropy change to ultimately becoming isentropic as n goes to infinity in this expression here. So have you got that? Do you understand what I'm saying? You sure?
But how do you physically, I mean, if I say that the entropy has increased significantly, what does that tell you physically? I've always struggled to, I'm saying from a designer's perspective, I say that entropy has increased a lot.
It'll tell you that the total pressure has gone down. And if the total pressure goes down, then that's a minus for you. You're losing the total pressure that drives the flow.
It's unsurprising because gradual changes are always better.
Yeah, and yes, it's not too surprising that as you make small changes, even though they accumulate to the same as one big change, you keep the flow nearly isentropic.
You make n go to infinity by a rounded.
Yes, here is it. Here's it. You make every one of these steps delta theta. D theta. The smallest change in theta that you can put into a computer. The last digit of a 7-digit number. Okay. So now you can see something interesting here. If I did this near a wall, what would happen? I'd have these set of marked lines where the marked line, sine of mu is 1 upon the Mach number. And now this is compressing, so the Mach number is going down. So these marked lines are lines that look like this near the wall. Well, what can you see? Is that even though this flow way down near the wall here is isentropic, these lines are going to cross. And that is wave breaking in characteristic terms, just the same as for those of you who surf, you know that as you get near the beach, the height of the wave, it gets higher and steeper because the speed locally of the wave is the square root of GH for this wave, and so the wave tends to speed up and you get breaking, and surfers are all happy. In this particular case, you replace the breaking wave by a shock wave, a discontinuity. Okay. So the same delta theta, m is decreasing, therefore beta is increasing. And these characteristics, these characteristic lines, the m shocks become Mach lines along which theta and m are constant. And beta, the angle of this, is between mu and pi on 2, and for weak shocks it's nearly mu, and sine mu is 1 upon m. And so as theta as the turning of this flow becomes weaker and weaker, then these become Mach lines, they're called, along which the Mach number is constant. And so I've told you here, farther from the wall, the Mach lines converge and a shock is formed. And so out here a shock is formed, and now you'll have a jump, a change in entropy across the shock, but way down near the wall here, you'll have an isentropic compression in a curved channel. So if this is a curved channel, you'll have an isentropic compression. All right, so if it's now isentropic, instead of going from left to right and going and compressing, so this is a compression here, I am going to reverse the flow and take it back this way and go through an expansion. So that's an idea. So here's what I'm saying. So here are these Mach lines here, and here's the flow coming along, and it gets compressed and it comes out here. So now what I'm going to do is turn this flow around. Because it's isentropic, I'm going to reverse everything, and I imagine a flow that's coming back this way. And I've got an infinite number of weak shocks, so it's isentropic. And of course, I've said here on the right, of course, a discontinuity is not possible because U2 can't be greater than U1, and that would be the case. And that would imply a decrease in entropy, and so we can't have discontinuities, but maybe we can have a continuous change. So I've just drawn this figure around the other way. So the flow's coming in here and it leaves here. So this is an expansion. And these are the Mach lines. And you can see that they're getting further apart when I go in the other direction. So it's an expansion. So these Mach lines don't converge. In this case, they diverge in the expansion. So we'll see how we're going to use that in a minute. But it's analogous to an expansion fan, which I think I really talked about but didn't really derive in the XT diagram for flow in a tube, the shock tube problem. The Mach lines are divergent, that is, the expansion is isentropic everywhere. All right, so now let's see what we can do with that. Now, if the flow is isentropic, well, you've seen me write this down before, but how did that arise? That came from H naught is equal to H plus a half U squared. And H is CPT, and CP is gamma R over gamma minus 1. So H is for a perfect gas. So H is gamma RT over gamma minus 1. And that's A squared over gamma minus 1. So if I divide H naught, so that's CPT naught, and if I divide the right-hand side by H, I'll have CPT naught over CPT, and the CP's will cancel, so I have T naught over T, and then I have 1 plus, and then instead of H, I can write, so I'm dividing by H, and I can write that as A squared over gamma minus 1, so it's a half U squared divided by A squared over gamma minus 1, put the gamma minus 1 up there, and U squared over A squared is M squared. So that's easy. So that's T naught over T is that. Now, what is P naught over P? Well, that's easy to do. P goes like rho to the gamma, and rho goes like P over T. Rho goes like P over T. P is rho RT for a perfect gas. So it follows that P naught over P will go like T naught over T to the gamma over gamma minus 1. So I write that down. So P naught over P, or P over the total pressure, PT, or P naught, will be 1 plus gamma minus 1 over 2 m squared to the minus gamma over gamma minus 1. All right, so now let's take logarithms and differentiate. So if I take logarithms and differentiate, I have the total pressure, it's isentropic, the total pressure doesn't change. So the total pressure is a constant, and so I have the logarithm of P minus the logarithm of PT, so that's just a constant. And I differentiate, logarithm of P, I get dP over P, and I'll have a minus gamma minus 1 times the logarithm of this thing, and if I have to differentiate that, I'll have gamma minus 1 by, and this will be 2 mdm divided by this thing here. So I have minus gamma minus 1, and I differentiated this, and I get gamma minus 1 mdm. And so since d theta is the square root of m squared minus 1 over gamma m squared dp over p, I can substitute this, and this gives me the Prandtl-Meyer expansion. So you can, Ludwig Prandtl was a very clever chap, and he worked this out. And so d theta, I've got, for this dp over p, I've got this expression of Mach number, so I've put it in here, and I've cancelled the gammas, and I put the minus over on the left-hand side, and then I integrated. And I've integrated this right-hand side, so this is square root of m squared minus 1 over this quantity here. And this mdm is d of m squared over 2. So you can see that this becomes easily integrated if I replace m squared by y, for example. And I'm going to integrate it, and I'm going to call this the Prandtl-Meyer function nu. And this is a function of Mach number, and I'm going to integrate this from 1 up to Mach number so that this thing, when the Mach number is 1, is 0. And I integrate this left-hand side, and I get minus from the minus here, minus theta plus a constant. And I don't know what that constant is, but you can see that this is a very interesting result. So this is a result for isentropic flow. It'll be true for an expansion where the characteristics, the Mach lines, don't cross. Won't be true for a shock wave. So nu as a function of Mach number is called the Prandtl-Meyer function, and it's such that nu is equal to 0 where m is equal to 1. When this is equal to 1, then obviously this thing is 0. And so minus theta 1 plus a constant is equal to nu times at Mach number m1. And in general, minus theta minus a constant, plus a constant, is nu of the Mach number m. So one minus the other. Theta minus theta 1 will be nu of m1 minus nu of m. And theta is positive in the direction of a compression, namely where the Mach number goes down. So how do you use this thing? So if you're given m1 and delta theta, how much you're going to turn this flow in an expansion, you can look up this table of the Prandtl-Meyer function for a function of m1, and then you know what the change in the Prandtl-Meyer function is for the change delta theta. You're going to change delta theta by so much, so this change in delta theta is going to give you a change in the Prandtl-Meyer function, and so you're going to get a new you know what the new Pranamaya function is, given what delta nu is. The new Pranamaya function, and that's a function of Mach number m2, and that gives you m2. So let's talk about some examples. So what if I had the intersection of unequal shocks? Well, what would happen? Well, so I'm going to turn these two flows differently. So who knows what's going to happen? That's right. The shock polar won't be symmetrical. And I'll have to be careful how I use the shock polar, and I haven't quite explained that as well as I should have done. So we're going to turn this flow, theta 2, so we know what the conditions are in region 2 here. And we're going to turn this flow through theta 3, and so we're going to know what the conditions are in region 3. What we don't know is what is region 4 and region 5. All that we know is that they have to be at the same angle. So what you have to do is match the pressures and the angles across this slip line here between these two flows. They won't have the same velocity and they won't have the same temperature, but you will have to match the pressure across there. So how do you do it? And here I've imagined what might be an intercept here of these two shock polars, one constructed here at 2 and the other one constructed here at 3. But I have to match the pressure, and I haven't really made that clear from the intercept here. I have to match the pressures at that point and match the angle.
Sorry, but how did you know that the pressures would actually be matched but not the velocities?
Ah, that's a good point. It's because I want to have a condition that I could imagine is physically realistic. I can physically realistically have the same pressure above and below and a slip line between one flow and the other.
Yeah.
It's an imagined solution. It's an imagined inviscid solution.
Yeah.
And if the flow were truly inviscid, then that would be an acceptable solution. Otherwise, if one had a vertical velocity and the other one didn't, that doesn't make any sense. Inviscidly, it doesn't make any sense. So the only inviscid solution would be a discontinuity in velocity, a discontinuity in temperature, discontinuity in Mach number, speed of sound. It's not like the symmetric case.
And it's because pressure acts in all directions, so the pressure has to be continuous? Yeah.
The pressure has to be continuous across there. Yeah.
It's pretty subtle.
It is subtle. It is subtle. But what could you do if the flow were inviscid? And this is what you would calculate. So how does it work? So I'm given M1, say, and I'm given theta 2, how much I'm going to turn on one side, and how much should I turn on the other side. And maybe one of those is 0. I don't turn it at all. Then I get the beta from 1 to 2, and the beta from 1 to 3, and I get M2 and M3. And now I'll have to choose, and I don't know in advance what theta 4 is going to be. I have to choose an angle. I choose a theta 4, and I have a theta 4 minus theta 2, and that gives me a beta 2-4 for this M2, and a P4. And if theta 5 is now going to be equal to theta 4, then I have theta 5 minus theta 3. It gives me a beta 3-5, and that leads to a P5. And if I don't match the pressures, I got the wrong theta, and I have to iterate. So I'm into a computer program to do it. I got to iterate. But you can see physically what happens. So I've sort of sketched it over here, but this is not really right, because these shock polars, depends how you non-dimensionalize them. But if you multiply by a half rho U1 squared for in each case, then you've got to match the pressures at 5 and 4. All right. So now here's another example of what could happen. Let's suppose you had a double corner. So you turn it through theta 1 here, and then you turn it through theta 2 here. What happens? Well, right out initially here, I have this flow will turn, and I'll have another shock wave here from 2 to 3, and the flow will turn again. So the flow is now going in this direction here, and here it's going in this direction, and it's all the way in this triangle here. But this beta intersects this beta here at this point here. Beyond that point here, we could have a single shock wave which would turn the flow. But I don't know how much to turn the flow. In a perfect world, I'd turn the flow exactly the same as I'd turn the wall. But I don't know whether that's the right solution. And it may not be. And in fact, there's going to be a slipstream here, because this flow is being through one turning angle, whereas this flow below this line is being through 2 shock waves. So it won't, in general, be at the same temperature, and it won't, in general, have the same velocity. So I have to choose a theta 4, just like I did in this problem here, and I have to iterate until these 2 pressures are the same. And coming away from here will be a weak reflection coming from this intersection here, because this flow may not be at the right angle, theta 2. So I might have to have a weak reflection to get, and P3 won't be equal to P5. So I have to have another weak wave here. And that weak wave could be a compression or an expansion, depending on theta 1 and theta 2. And it can be either. So it's quite complicated. And you know, you can do it with the shock polar, but it's a local region. The important point is that these 2 shock waves here become one shock wave beyond this point here. So these characteristics merge. So you turn the flow through a single shock wave here, but when you turn it through a single shock wave from this direction to this angle, you don't know what that angle is in advance. And so there'll be a slipstream there. And there'll be reflected waves, and it's complicated. All right. So this is what happens. So here is where you start off, and then you turn through theta 1, and you draw another shock polar, and you turn that through theta 2, but you're not on the same shock polar as the initial shock polar, but you have to get on it. So you have to draw another shock polar, and you have a small wave here that will get you back onto the same pressure as you had for the first shock polar. All right. Now, how do you get supersonic flow? What is the attenuation of a shock? So now, let's suppose that we have an expansion around this corner here. So we're going to imagine the flow is coming along here, and then I have a small radius here where the flow is turned back horizontally. Now, you can imagine that it's an expansion. It's locally an isentropic flow where all of these Mach lines diverge. So this is an expansion. And so this is an expansion. You have these Mach lines here that diverge. And so this expansion will have to reflect, and this one will have to reflect, and this one will reflect, so there'll be weak reflections. And the Mach number here, as you go from 2 to 3, the Mach number will increase because it's an expansion, so the Mach number gets higher. So we came along here, we compressed, and the Mach number went down, and then we turned it, and the Mach number goes up. So, and now I think this comes close to your question at the beginning of the class. What actually happens for a wing that looks like this? So here's a wing. So let us suppose that it's a sharp wing. Now, subsonic don't have sharp wings, but in supersonic flow you could have a sharp wing, or you could have a flat plate. And we'll think about that in what I'll say next. Okay, let's suppose this angle here, initially right here, this is a sharp leading edge, and this turning angle is less than the maximum value. So this flow is still supersonic in this region here. And let's imagine we have a Mach wave here. And then we have to turn it some more, and we have another Mach wave. And here's one here, and then we turn it some more, and we have another Mach wave. These Mach waves are diverging. This Mach number is, as I turn the flow, I'm expanding the flow, and the Mach number is going up, and the pressure is falling. And then I'm coming here, and these Mach lines are still expanding, but then I get to this point here, and because I have a flow coming from here, it has to be horizontal. What is the only way I can do that? If this is a high Mach number here and I have to turn it, I have to turn it through a shock wave. So I have a shock wave here, just as I had a shock wave here. Shock wave at the end. And so, what does the pressure look like? What does the pressure look like on that airfoil? Nothing like what would be true for Mach number 0. Nothing like it. What I would do here immediately is that I'd have a shock wave and the pressure would rise. And then I have an expansion all the way from here, all the way around there, so the pressure falls. And then I have another shock wave and the pressure rises. And I come back, and if the shock waves are not too strong, I come back to the same pressure as I started with, very closely. So that's typical. This pressure distribution is typical of the far-field N wave that you've heard about. Concorde had an N wave, the sonic boom. So the sonic boom is a shock wave here and a shock wave here. And they don't go away. Doesn't go away. And let me compare that with Mach number 0. What happens at Mach number 0? At this point here, the flow's coming along and it's turning. So this is a compression. You've seen that in your inviscid flows course. If you turn the flow, you'll have a stagnation point. So the pressure will rise here, and then you'll have some sort of symmetry pressure distribution if it's horizontal, and the pressure rises again here because you have to turn the flow back horizontal. So the pressure distribution for Mach number 0 looks like that, and for supersonic flow looks like that. Completely different. And that is what the sonic sound barrier was all about. And that is why the aircraft went into the ground. And they did. You were too young to know it because it happened before you were born, but I remember it. Headlines: sonic barrier, and yet